and this time planes in space. If a line in R3 is defined by two linear equations and it's in symmetric form, and what kind of a set is defined by one linear equation? It turns out that is a plane. And so this is always a big source of mix-ups. When you see there are two sets of linear equations, either written as x minus x minus a value divided by a value equal to y minus a value divided by a value, and z minus a value divided by a value, or as one of the variables equal to constant and an equation of the other two, or two of the variables equal to the constant. Those are the symmetric forms of the lines in 3D space. But for a plane, you will have only one linear equations of all three variables. Sometimes the one variable or two are missing, but and it's just one linear equation. So here are the examples. X equal to 0 is just, where is x equal to 0? All the values on in zy plane. See, x equal to 0 is just the zy plane. What is z equal to 1? Z equal to 1 is the plane parallel to xy plane. What about y equal to z? Y equal to z is the plane that actually contains the x-axis, and if you look at it through look at how it projects on YZ plane, it just gives you y equal to z on that plane. Y equal to negative z, again, and contains the z-axis. And if you project it on if you basically projecting means that you look at it as in x-axis is just an arrow coming at you, and that's a projection. What you see is going to be your projection, and through that projection it would be just y equal to line y equal to negative z. So that's a plane whose projection on YZ axis is just the line y equal to negative z. So how do we translate between the algebraic equation of a plane and its geometric properties? How do we basically figure out the equation of a plane? Let's start explaining how this works. When you're talking about the equation of a plane, you sort of want to have a point on the plane and a vector that is orthogonal to the plane. And so in a non-zero vector that is orthogonal to the plane. So and having the in one unique orthogonal vector, the non-zero orthogonal vector, and a point gives you always a unique plane, and so that's enough. It's like having 3 points on a plane gives you a unique plane, and 3 non-linear, non-collinear points gives you a plane, and so on and so forth. So this another way is having the orthogonal vector and a point on the plane. Now let's see how does this help us write the equation of the plane. And so let's say P on the plane and a point on the plane. How do we show any point on a plane with x, y, z, right? And so let's say we have, instead of a point, we put it in format of a position vector. And so r equal to position vector x, y, z. And so that's the point. Now connect P and P0 to form a vector P and P0. What happens to, and that actually is going to be the position vector of P. See, P0, P is position vector of P minus position vector of P0, as we know from the past. Now, this position vector is actually, and remember, n is orthogonal to the plane. That means it's orthogonal to any line vectors on the plane. So n has to be orthogonal to this. What do we know from just a few slides ago is that when the two vectors are orthogonal to each other, their dot product is going to be 0. So you write n times r minus r naught equal to 0. But what is r? R was x, y, z. What is r naught is just the point on the plane, x sub naught, y sub naught, and z sub naught. And so if you write it out, it becomes the first coordinate of n times x minus x naught, the second coordinate of n times y minus y naught, the third coordinate of n times z minus z naught equal to 0. And so this would be the equation of the plane, and this is how you set it up. The vector n is called a normal vector to f, and not any non-zero multiple of n is also a normal vector to f. I click on question F. The vector k is normal to which of the following planes? K is the one that is parallel to z-axis. A, x equal to 1, B, z equal to 1, C, z equal to 1, D, x plus y equal to 0, E, x plus c equal to 0. So let's think about it and come back. So here's the x, y, z plane. Remember, another thing to mention about x, y, z, axes, and when you write down, it's always x on the left and or x in this. Basically rotates in this direction, x then y then z if you're going counterclockwise. So we're saying that x, y, z, this is the most common way how we set up the axis. Not always necessarily that way, but it's a good idea to do it in that order. Counterclockwise x, y, z, and so and then now let's see, k is in this direction. So where is it perpendicular to or orthogonal to? It's orthogonal to any plane that actually is parallel to xy plane. And what are those planes? Those planes are basically z equal to a constant. Any other way of discussing that? Well, you can also say k is equal to 0, 0, and 1. And then however you want to write out the equation of a plane, it's going to end up with 0 times x minus x naught plus 0 times y minus y naught plus 1 times z minus z naught equal to 0. And that will give you z equal to a constant, and that's c. Equation for planes example 4. Find equation for the plane containing the point 7, -8, and 5 with the normal vector 1, n is equal to negative 2, 1, and 4, 2, n equal to negative 2, 0, and 4, and 3, n equal to 0, 0, and 3. So point is given, and there are 3 planes that we're finding. So in the same, the planes that go through this point and are perpendicular to one of these. Let's start with the first one. So how you do it is you write down, my rule of thumb is that I write down, this is negative 2 parentheses plus, because this is we're dot producting the n with the position with the vector on the plane, which would be containing x and that point, basically a vector with those two. And so, and then 1 times the second plus 4 times that equal to 0. Then I put in what goes inside x minus 7, then x minus 8 plus 8, and then, oh sorry, y, then z minus 5. And so that gives me the equation of this plane. And then you can go a little further and basically distribute that negative 2 inside. You get negative 2x plus 14. And then here you don't have to distribute the 1. Here you distribute 4. You solve and you put all the x, y, z on one side and the constant on the other side. And that's another format of that's the one that people are more familiar with. But this is also an equation of the plane. This is an equation of the plane, and same I guess routine when you're finding an equation of a line, you can solve for one variable or not, and here you solve for 3 variables on one side and the constant on the other side. Now how do I do 2? 2 is the same routine again. You multiply the direction vector by a vector on the plane. And so again, x minus 7, y plus 8, and z minus 5. And this time around, because you have a z multiplying y plus 8, y completely disappears. And so this equation of plane had all 3 variables. This one only has 2. What if 2 zeros there? When you have 2 zeros there, like the iClicker question that we did, you get 0 multiplied by x minus 7, 0 multiplied by y plus 8, so x and y disappear, and you end up with a z equal to a constant. Okay, we discussed that 3 non-collinear points are, and they give you a unique plane, right? So can we do something to find the equation of the plane going through those 3 points? And so example 5 is just that, and you're finding the plane that goes through a point A, that is 1, negative 2, and 0, point B, that is 3 and 1 and 4, and C, that is 2 and 1 and negative 2. So how do I deal with this? Then I need to have a point and a normal vector, right? And these are points on the plane, but I have 3 of them. I can form vectors on the plane. How do I get from vectors on the plane to a normal vector? By cross product, basically. So that's one way of if I already have 2 vectors, one of the best ways of finding a vector that is orthogonal to those 2 vectors is to find a cross product, as we learned in the cross product section. So I form, basically I form AC, which is AB, which is vector AB, which is the difference in here, 3 minus 1, 1 minus 2, 4 minus 0. And then I find IAC. There are 2 vectors that lie on the plane F. Now I cross product them to find in this cross product to find the basically you need normal vector. How do I cross product? As we did in the previous part, it's just I, J, K, and then the two vectors go in here, and you find the determinant. And when you find the determinant, you end up with, so let's see, I, and then it's 3 times -2 minus 12, and that is -18 minus, and then here 2 times -2 times -4, which is that's J times -8, and then negative signs basically clean each other up. And then for K you get 2 times 3 minus 3, which is 3K. And then when you clean it up, it's minus 18I plus 8J plus 3K. And so minus 18, 8, and 3. Okay, now that we have a normal vector, which is the cross product of the two vectors on the plane, and we have point, I actually have 3 points, I just need one. Use one of the points and the normal vector to find the equation of the plane. Again, you write down the normal vector and parentheses in front of it. And if you use A, for example, you get in the parentheses, you get x minus 1, and then y minus 2, which is y plus 2, and then z minus 0. And there are other possibilities. You can use point B and you get of this form. The funky thing is that if you use the same normal vector and you find this equation or that equation and you simplify it so that all the variables are one side and the numbers are in the other side. So if you preserve the normal vector though, without simplifying anything that relates to normal vector, the constant on the other side is going to be the same. I-clicker question G, find an equation for the plane that passes through point 3, 2, and 7 and is parallel to the plane 2x minus 5y plus z equal to -1. So let's take a minute and solve the problem and come back. A point is given and a plane that is parallel. What does a plane that is parallel mean? That means that if they actually two parallel lines or parallel planes, they have the same normal vector, right? And so the normal vector here, I can extract the normal vector 2. What is multiplying x is 2. What is multiplying, and all three variables on one side. One is multiplying y is 5, and what is multiplying z is 1. So that's a normal vector, and that's a point on the plane, so I can write it as 2 times minus 5 times, and then 1 times equal to 0. And then I can put in x minus 3, then y minus 2, and z minus 7. And then I can solve this and clean it up. There are a few options that don't have the same. See that this is the normal vector, and so this one is out because it's not the same normal vector. This one is out because not the same normal vector. I have to figure out between these two which one is the answer. The only way I can figure it out if I multiply everything through. So 2x minus 6 minus 5y plus 10 plus z minus 7 equal to minus 7 equal to 0. And that gives me 2x minus 5y plus z is equal to 10 minus 13, I'm sorry, 13 minus 10, which is 3, and C is the answer. So relative position of two planes in space. Two planes are parallel exactly when their normal vectors are scalar multiple of one another. If two planes are not parallel, then they intersect. So that there's no third option. Or two planes are the same. That's the only other one. When two planes intersect, their intersection is a line, and the angle between angle theta between the planes is the angle between their normal vectors, and it can be at most pi/2. If theta is equal to 0, then the planes are parallel. And so here are some pictures. For example, there is the x equal to y plus z, and x equal to y minus z is the green and blue planes, and they intersect in a line. And then z equal to 1 and z equal to -1 are parallel to each other. X equal to y plus z intersected the two yellow planes also, and the green plane also intersects the two yellow planes and both each pair intersect in a line except for the two pairs that are parallel. So now when we're talking about theta, here's the theta, the normal vector to the yellow plane, z equal to 1 is the orange vector here, and the normal vector to blue plane is the blue plane right here, the blue vector right there. And so the angle between those two, and we know how to find that angle through basically through the dot product. And so we can find the formula that we know and use it to find the angle between them. So example 6, determine the line L of intersection of the plane F1 and F2, whose equations are F1 2x minus 3y plus 5 is equal to 1, and F2 3x minus 4y equal to 7. And so where do we start? I have two planes, and then each one of them have a normal vector. And remember, any line on each plane is perpendicular to the normal vector. So the normal vector of F1 and normal vector of F2 are both perpendicular to L. Oh, two vectors perpendicular to another vector, right? So the normal vector of this and this are perpendicular to the direction vector of L, and therefore I can cross product here, cross product this normal vector with that normal vector, and so I have n1 and n2. First extract them. Normal vectors are these coefficients, and normal vector here, coefficient here, and then you cross product those, and you get the normal vector, you get the direction vector for L. But you need one extra piece of information. That's a point on L. Otherwise, you cannot write the line. To get a point on L, because the intersection of these two has many points, you can actually find infinitely many points in there. And so a lot of times, basically people recommend setting one variable equal to 0, and then finding, here we set z equal to 0, for example, and then we solve an equation to find x and y, and we get 17 and 11 for x and y. And so you have to solve the system to get infinitely many solutions, but you can also set one of the if you remember from solving system of equations with infinite solutions, you can always set the free variable equal to whatever you want and get one solution out of the infinitely many solutions. Anyway, so you use that normal vector and the vector cross product of the normal vectors, which is the direction vector, and you write multiply it by t, and then you add it to the point on the plane, and then you get the equation of the line of the intersection.